Before moving on to talk about shaders, I'd like to use this time to fill a few gaps that we left when we discussed our full program in the last lecture. So I'd like to add mostly a little bit about viewing and why don't we have transformations and how this 2D fits into a 3D setting. One of the things that you're going to come across as you start working in web applications is that the execution model that I mentioned last time is somewhat different from what you're used to when you compile a program, link it, and then you just run the program and it has control. You're in a much more complex environment on the web, and so for now we're going to say what the part we need to know is just that we start with this HTML file. These files are read in order. The code is executed, and we can start and what happens next is based on this onload function, which just says when you've loaded in or read in all of the functions that are in that HTML file, now go to this point and start executing. Now what will happen next in a more typical example is that we will have things happening. We will have a mouse, we'll maybe enter some information with the keyboard. And so these kind of events, the pushing of a mouse button, the pressing of a key, will cause some actions to happen. So that once we've executed all the initialization, we'll be in some sort of an event loop that's within our browser waiting for something to happen. Now in our first example, because there were no events that we discussed, it will just sit there until we kill that window. But we'll see more of this as we get on to our next programs. Now what's more important here is that we have not talked at all about coordinate systems, and the numbers that we put in were kind of magical. Why were they 0.5? Why did that come out correctly on the display? So generally, if we go back to the original OpenGL when there was a fixed function, in the specification it named a number of coordinate systems. Because of that, many of these functions have been deprecated. We have a lot more flexibility here, but with WebGL. But I've taken the tack that we should follow those coordinate systems because they're very useful in trying to build our models and implement the synthetic camera model. So the ones the one that we start with is usually called world coordinates or object coordinates, or sometimes problem coordinates. And the idea here is that when we go to what's called device-independent graphics, we would like to be able to work in the units of the problem and not worry about some artificial units that have to do with what's the numbering of the pixels on the screen, or in the old days with analog displays, you actually had to enter the information in terms of inches across the screen. The conversion to whatever the implementation needs and the particular device needs is something that should be happening within the graphic system and should not be or anything we should have to worry about. So we'll start off with object coordinates. That's the term we'll use most of the time. There may be a level above that called model coordinates, where if we have some complex objects and we build them up out of parts, and the parts may be in some standardized system, which we'll call model coordinates, then we'll do some sort of transformation to bring them into our model world and into object coordinates. But for now, we can say we specify our objects, the vertices, in object coordinates. Now eventually, because we're interested in what the camera sees, we're going to have to do something to specify the camera, and that'll bring us into what's usually called eye or camera coordinates. But those specifications of the camera, as we talked about a couple of lectures ago, will be in object coordinates. Where do we position the camera? How do we orient it with respect to whatever coordinate system we're using for our objects? But eventually we're going to go into window or screen coordinates, because we do produce pixels, even though we probably won't see them in most applications directly. We'll also be talking about some internal representations the one that's most important to us is clip coordinates. And the reason that that's important is that the vertex shader is required to output in clip coordinates. Now, very simply, what that does, and we'll see another picture of this in a couple of minutes, is that everything that's within a cube, whose sides are length 2, and whose origin is at the center of it, and so it goes, the diagonal, the principal diagonal goes from -1, -1, -1 to 1, 1, 1. Everything in that cube in clip coordinates can be visible. You know, things may be blocked by other things, but everything outside of it we know won't be visible and won't be displayed. And that's why it's called clip coordinates, because everything outside of that box will be clipped out. So the basic job of the vertex shader is to convert everything into clip coordinates. It may be doing other things, but whatever units we were using within our object or world has to be converted into clip coordinates. So the little trick we pulled at the beginning was to say, okay, let's specify things right now in clip coordinates. That's why our cube or square had coordinates from one corner was -0.5, -0.5, and the opposite corner was 0.5, 0.5, which put it sort of halfway inside of that box within the plane z equals 0, which is also inside of that box. So it just avoided doing a lot of transformations which we're not quite ready for. Okay, so we have to output in clip coordinates, and the input to the fragment shader from the rasterizer is said to be in window coordinates. We won't see that directly, but basically those units will be in pixels numbered from 0, 0 up until the maximum number in the upper right corner. Now, as we said, when we looked at our simple shader, there was a variable called GL position, and that's what our rasterizer expects the values to be in. Now, what about viewing? You know, we didn't have a camera. Why didn't we have a camera there? Well, we sort of defaulted in a way. So WebGL starts off with a camera that's at the origin in object space, and it's pointing in the negative z direction. And be careful with that, because sometimes you're going to have the camera pointing in the opposite direction and you won't see everything. Because if it's looking in the negative z direction, then it's tending to see things with negative z values. And the orientation is the y direction is up, and the x direction goes to the right, and the z is kind of a depth direction, measuring how far we are from the camera. Here's the default viewing volume, which is that box and clip coordinates, which by default will have one corner being at 1, 1, -1 here, because this is the negative z, and this corner will be at -1, -1, +1 in the positive. And so since we specified everything in the plane z equals 0, since we didn't specify z values, automatically WebGL says, oh, you must mean that the z is 0, and so it stores those values, for example, as 0.5, 0.50 when we specified a vertex at 0.5, 0.5. So that's how we start, so we didn't worry about that because we rigged our numbers. If we look at the default viewing, it's even nicer. The default view is what's called an orthographic projection, in which the projectors are parallel and they project in perpendicularly into the plane z equals 0. So anything that's along, let's look at this projector over here, we have a point xy0, it projects into xy0. So if we're within this box, any point over here within the box will project onto this plane in the middle, keeping the x, keeping the y, and making the z equal to 0. Well, we started with z equals 0, so in a way what we're doing is we're using the fact that the plane z equals 0 is really within this 3D space, and by specifying things with just the x's and y's, we're really embedding ourselves within a 3D world. The viewport we had in there was the whole screen, but in general the idea is this, that you specify a window up on your display, and that window may be used in multiple ways. It may be used by other applications. It may be used to produce multiple images. So for example, people who do what are called multi-view orthographic projections. That's where you have, if you're doing architecture or construction, you have a side view, a front view, and a top view, and you put one over here and the other two down here. So you can think of that as forming three images. Each one is assigned a different region of the canvas that you created, and we use the viewport to say how much do we want. So we specify the lower left-hand corner over here and the height and the width of that viewport, which is inside of the canvas that we specified in our initialization. Now, we haven't talked about transformations yet, but let me just give you a couple of the options, because the way that we're going to do two things. One is to convert into clip coordinates in the vertex shader, and also to do the projection, which is part of what goes on in the vertex shader, is going to be doing some kind of transformation. We use the idea that every change of a coordinate system is equivalent to some sort of a transformation, which we'll see will be a 3x3 or a 4x4 matrix. Now, before we went to OpenGL 3.1, we had a whole bunch of transformation functions that were in there. We could set specific kinds of transformations, like translations and scalings and rotations, and we could set certain kinds of viewing transformations to get the standard perspective and orthogonal views. All those functions were deprecated. So you have three choices of how to do it. One way is to put it in your application code, to just carry out a transformation within your application so things project correctly and they're in the correct system. It turns out that'll be the least efficient way to do things, because we'll wind up burdening the CPU and creating some bottlenecks in an interactive application. The second way is to do it within the shaders using various functions in GLSL, which is fairly straightforward because it has as basic types, it has matrices and vectors. The third way is to use some of the functionality in mv.js, where what we've done is to take most of the deprecated functions that were used to manipulate matrices and vectors and put them into mv.js, so you can get all of the standard matrix and vector operations out of that and some of the viewing operations. But of course, this is running in the CPU, not the GPU. But these are the two ways that you'll probably be doing things. Now, what I want to finish today with is doing a little bit about what's going to be your first assignment. We have most of the pieces, so you should be able to get started on this using the code we've been talking about in these lectures, and also code that's on the website. But this first is a cute example. We're going to do this in 2D, just so you can get started and before we have a more in-depth discussion of 3D. And so let's start with this basic idea. Here you are, you have a point in the plane, and this is 2D. So if you rotate that point around the origin, it's very easy to show that the new point, if you rotate by theta degrees, is given by, its x value is given by x cosine theta minus y sine theta, and the new y value is given by x sine theta plus y cosine theta. There's a derivation a little bit later in the book, and it's easy to prove that to yourselves. But now I want to give that a little bit of a change, and we're going to create something called twist, where we say that the amount of rotation, see, this is going to rotate every point wherever it is by the same amount. What if we make the amount that we rotate change by a factor that's proportional to how far that point is from the origin? Okay, we might put a little constant in here, but that's not going to change much. So the idea is that points that are near the origin don't rotate very much, but points that are very far from the origin rotate a whole lot. And I'll show you what kind of things you can get out of that. And it's very simple to do. So here's an example where you may want to do it within the application code, so it'll be executed in the CPU. But you can also do this, and I'd advise you at least try this, and probably best to try it both ways and compare, is you can easily do this within the vertex shader. So let's look at what happens here. So let's consider just a simple triangle, 3 vertices to specify this triangle. That's easy. And if I rotate it, this is what I get. Now, what if I rotate, if I do twist here? So the amount of rotation is proportional to how far I am away. Well, that isn't going to change anything because everything was determined by these 3 vertices, and these lines connecting them and the edges and the fill in between was all based just on these three vertices. So no matter how you do this and how you apply the twist, the angle may change, but you're still going to get something that looks just like a standard triangle. So the trick here is to tessellate that triangle and convert it into a number of smaller triangles, and then apply rotation to the vertices of each of those other triangles, and then fill the thing again. Now here's a tessellation. Now how do we do that tessellation? This has been tessellated 4 times. One way is to use recursive subdivision. So if you've been reading the book and looking at our examples of with the Sierpinski gasket, when the second way we did it was to use a recursive subdivision. And if you just change that about 1 line in that code, you can derive this kind of a recursive subdivision for triangles. Now look at what happens if I rotate each of these inner triangles using the twist, with the idea is now here's the origin in the middle. If you're further from the origin, you're going to rotate more. So I rotate, so these guys are going to be rotated out here a lot more than the ones over here in the center. And now I process a lot more triangles through my system. This is a good way too to test how well and how fast your system is. And I fill them so I won't see any of these edges anymore. And look at what I get. I get this beautiful curve here. And you may want to try this on other shapes. It comes out really nicely with some shapes and not with others. You have to be careful to put in this proportionality constant over here so you don't make this too big for points that are far from the origin, because it starts twisting around upon itself. Actually, you can get some wonderful shapes out of this. But this will give you an idea of the power of both this idea of recursive subdivision and tessellation, and our ability to create surfaces that look a lot more interesting from very simple ideas and constructing them with triangles. So let's get started with that, and we'll see more pieces of this over the next week or so.